Hi, welcome to Sam's Maths Lectures. This is now my fourth lecture on set theory. Okay, so far in axiomatic set theory we've discussed 6 axioms. So we've had sort of the axiom of extensionality that tells us when two sets are equal, the axiom of the empty set, which provides us with the empty set. So that's the sort of first explicit set that we're given. In fact, it's the only set, the first explicit set we're given. Then we are given the pair set, so we can create things like this or this. Okay, that was our third axiom. Then the union, which allows us to combine sets in more than just pairs. Then we had the axiom of replacement, which allowed us to map a set into another set using a functional relation. And finally the axiom of the power set, which allows us to take a set and then take the set of subsets of that set. So the issue with these axioms so far is that they only give us finite sets. It sort of tells us that there is one set that there definitely is, and that's this empty set here. And it tells us that there are other sets that we can build from it, but importantly, if you apply any of those axioms to a finite set, you're going to end up with a finite set. And the problem with that is that there are a lot of infinite sets that we encounter sort of every day in maths. So the natural numbers are infinite, the real numbers are infinite, and so many other things are infinite. Obviously we don't want to get too infinite, because something like the universe of all sets is not a set but is most definitely infinite. But we need some form of infinity. And so our next axiom gives us the most basic of the infinite sets, and so the axiom of infinity gives us a set. And so if we take, for some set x, and we say that R of this set x, so this is a functional relation, R is the set of x, the pair set of x with the set containing x. Okay, so then this is a functional relation, and we can call this S of x, so the successor of x. So the axiom of infinity says there is a set containing the empty set and also the successor of each element of each of its elements. Okay, so basically there exists some x such that the empty set belongs to x, and for every element y of x, the successor y is also an element of x. Okay, and so this is infinite because obviously we can keep adding a new element each time, it doesn't terminate. So we've sort of got the empty set, the successor of the empty set, and then the successor of the successor. So that's going to look like this. Is that the correct number of brackets? I think. Okay, something like that, and so on. Okay, and that keeps going. Okay, so this is an infinite set. Obviously, writing out these elements gets more complicated each time, but it does keep going forever. Okay, and so we can, in fact, form the natural numbers, so 0, 1, 2, 3, and so on, from these. So we can take, we can call this element here 0, and then this is 1, and then this thing here is 2, and so on to infinity. And so this gives us the non-negative integers, or the natural numbers, n. Okay, and so we have sort of the successor of n is a map that takes n into n. We'll talk more about what maps mean later on, but it sort of defines the integers and how addition works. So we start by adding 1 each time, and then we can add 2 by adding 1 twice, and so on. Okay. Yeah, that's about all there is to say for that. So this is the smallest infinite set. We'll talk more about the different sizes of infinity later on when we talk about cardinality, but this is the smallest possible infinity, and then the larger infinite sets are defined by sort of taking the power set of this, which is then going to be larger, and so on. Okay, so up till now the sort of 7 axioms have been fairly well motivated. You know, we need things to be equal, we need an empty set, because otherwise how do we take the intersection of 2 sets that are disjoint? We need all of these construction axioms because they're just fairly obvious, and we need this infinite axiom because we need infinity somewhere. So one that is less obvious or less intuitive is the Axiom of Foundation, or the Axiom of Regularity. Okay, so this one is easier to motivate by showing what it implies instead of what it actually does. Okay, so it's sort of corollaries of this axiom are much more important than the axiom itself. Okay, so what this says is that every set contains a subset, or contains an element from which it is disjoint. Okay, so 2 sets are disjoint if their intersection is empty. Is disjoint. Okay, so every non-empty set, because the empty set doesn't contain any elements, so it can't contain an element from which it is disjoint. Okay, so for all x, if x is not empty, then there exists some element a such that a is an element of x, and a intersect x is empty. Okay, so that's the axiom of foundation. So for example, if we take the set A, B, then we'll call this x, then x intersect A is obviously empty, so that's our element. But obviously we do have non-disjoint elements, so x intersect AB is equal to A, which is non-empty. Okay, and so what does this mean? Suppose some set A is an element of itself, then A intersect A is equal to A, which is non-empty, okay, because A contains A and the set of A contains A. So we have this non-empty intersection, so A is not a set. Okay, and so importantly, this means that the universe does not belong to the universe, because if the universe belonged to the universe, then it would be a set, but the universe isn't a set. So yeah, that's useful, because if the universe were a set, then Russell's paradox would then be using the axiom of restricted comprehension, so it would be allowed again. So we've gotten rid of that by saying that no set can contain itself, and therefore the universe cannot be a set. Okay. And we also have that there's no sort of infinite descending chain, so we can't have a family of sets x0 which contains x1 which contains x2 which contains ... to infinity. Impossible, as we know that xn, where n is a natural number. This is a set because we've sort of this is the functional image of the natural numbers, which we've already showed are a set using the axiom of infinity. Okay, so then would have no disjoint element. As xn always contains xn plus 1, and if we call this big set capital X, that is then contained within capital X. So X is not a set, and so therefore we cannot have this descending chain, and that seems sensible because we can't keep taking elements. There must be sort of a minimal element somewhere, otherwise we could keep getting smaller in a sense, which doesn't really work. Going the other way is fine because we can just take the power set of each element and then we get sort of a chain. X0 is an element of the power set of X0, which is an element of the power set of the power set of X0, which is an element of, and so on. That's fine, that's allowed. And indeed, the infinite set previously from the axiom of infinity is another counterexample to this. Okay, this has been quite a quick lecture, but it didn't really have that much to say. I just wanted to finish off the axioms. There is one more axiom needed generally to construct all of mathematics, so we've used the 8 Zermelo-Fraenkel axioms now. There's also the axiom of choice, or Zorn's lemma is the other sort of common axiom that we use to finish off maths, because this isn't quite enough. But I want to talk about more basic material before I get to that. Okay, cheers for listening.